Good morning, everyone. How's everybody doing? Perfect. Everyone slept well? So thank you all for being here today. It's been a long year coming up, building up to this event, and we're really happy that you all could make it and present your work and get to know the community. So if you have not already, we have a WhatsApp conversation where you can find information and announcements. Some of the workshops will also be organized on there. So please join the group and don't hesitate to ask questions on there if you ever get lost, if you need help getting to Brest or anything. All right, this is the organizing committee, so if we could please give them a huge round of applause right now. We have Gabriel, we have Salomé here, Quentin, Mathilde Martin, Mathilde Michel, and Virgile. They gave their best so this event could happen and unfold without any problems. And so yeah, this is the team that met last year in the first edition of the JJBAs, and we're close friends now. I can say it. Yeah. I hope. All right, so a little jump to the past. So this was last year. It was in Saint-Étienne. It was a great event, and some of the organizing committee from last year is here. So we're happy to have them back here at this time. And so we tried to grow the event as much as we could, and so we added a poster session, and we're broadcasting all the talks live on YouTube. So if you want to send it to your parents, to your friends, to anyone who might be interested, the link is on the website, and just copy and paste. Right, and so we also grew the event so that we try to bring people from around the planet. And we have a lot of people coming from America, Asia, and Europe mainly. And so we're all glad you could make it and be a part of this conference. And so just a little heads up, we're looking for people to take over. So if you want to organize this conference next year at your lab, abroad, wherever, come find us, anyone of the organizing committee, and tell us you're interested. And we're going to go towards a smooth transition towards the conference. It could be in 2 years. There's no pressure. It's just we want to keep the event going. It's a great event. It's a great conference, and it will be a shame if it stops this year. All right, so a little bit about where we are. We're here. And so this is a map of Brest. This is downtown. If you want to go there, there's a bus stop right in front of, I'll show you later. But you can take a bus to go to the center of Brest. And there's not a lot to do, but there's the Capucins, which is a great place. I don't know if some of you went to the event yesterday. We organized an event at Les Capucins. And then you can just roam around the city center. You have the aquarium Oceanopolis, which is one of the biggest aquariums in France. And then you have also a botanical garden a little bit north of here. And around, so we're here. I guess most of you already had a walk around the hostel, but here you have a lot of bars and restaurants if you want. You have the beach here, which you can try and have a swim if you're not too chilly. And just here you have the bus station that takes you to Brest by the main road. All right, a few quick rules. You may have noticed there's a lot of kids that are sleeping here as well, and then other people. So try to be quiet after 9 p.m., 10 p.m. so that they can sleep. Don't go to other people's dorms. We have dedicated hallways, so try to keep to them. And also, the staff is just great, so if you have any question and you cannot find anyone of the organizing committee, you can directly ask them. They'll do their best to help you out. All right, about the conference, I see most of the posters are up, but if you have not already put your poster up on the walls, there are there's a room right next door, which is also the coffee break room. You have posters there as well, and in the main hallway. As I said, the conferences are broadcasted on YouTube. If you do not want them to be available online after the event, you can come and find us and we'll edit them out. Otherwise, they will be automatically posted on YouTube. And then, furthermore, Virgile, which is right in front of me here, is the only member of the organizing committee which sleeps here. So if at 2 p.m. you have a huge problem, you can find him at room number 3. And I'm sorry for his roommates, but that's how it is. All right, so today, let's take a look about the event. So we have Melia, is she here? In the back, which is going to be presenting her creation, artistic creation. It's a little movie in coffee break, in the coffee break room. We have Camille here, who's going to be talking to us after lunch. So she's the plenary for today. And then at the end of the day, we have the poster session. And so we have dedicated 2 hours to it, but it's just to fill up until dinner. So go have a talk, go ask questions to people who brought their posters with them. Tomorrow we're going to have Gaëtan Richard, and I don't think he's here today. Ah, Gaëtan! Comment ça va? We have Gaëtan Richard, who's going to be the plenary tomorrow. And then we're going to have the workshops in the morning. Just a quick heads up, the deep learning workshop will start a little bit earlier. It might be 8:30, it might be 8:45, we'll tell you on the WhatsApp, but it might be a little bit longer than the others. And then I forgot to put her name. Is she here? Is Megan here? Okay. So we're going to have the plenary by Megan Wyman on Friday. And in the morning, we're going to have the General Assembly with the election of the new organizing committee. So you better be there. And then Friday night, for those who are staying until Saturday, we're going to try to have a drink all together in the city center or somewhere in Brest. So feel free to join us. All right. Quick little talk about other rules. So you may have noticed that after 9 p.m. you cannot exit through the main or enter through the main entrance. So if I come in the hotel at day, on the left you have this little hallway, and this is where you come in after 9 p.m. and until 6 a.m. I think. And you need your badge, your key badge, your card to get in. And please don't use this door during office hours, as there are all the hostel staff, which those are their offices. So please try not to use this door any other time than during the night. For lunch and dinner, please try to be on time. And you have to clean up after yourself, so just clear the table and put it in the kitchen, and then the staff will do the rest. But don't leave anything on the tables and clean up after yourself. Finally, when we leave on Friday morning, we have to empty the rooms by 10. The conference will still be taking place here all day long, but the rooms need to be empty. In the entrance, you have this box where you can put all the bed sheets and pillowcases. And if you just can fold the duvet and put it on your bed, that'll be great. And don't forget to give us your neck badges when you leave. Finally, I'd like to thank the sponsors who helped us create this event. It's thanks to them that we could make this event at only 20 euros with accommodation and lunch offered. So they help us. Don't hesitate to go have a look at their website and ask them questions. And finally, we're going to be able to start this conference with the impact of anthropogenic noise on vocal production. And this session will be chaired by Léo Maucourt and Mathilde Martin. So the chairs, please come to the front row on the right. And please also, when you come up for your presentation, do not trip on the cables. Be careful and watch your step. Thank you very much.
Okay, hello everyone. So let's start with this first symposium about anthropogenic echoes, tracing human impact on vocal production. The first presentation will be given by Mariane. She's going to talk about the impact of pollution on the cultural evolution of bird songs. Please, just a reminder for the question, can you please stand up and come to this microphone to ask your question? And that's going to be the way to ask the question during the conference. Thank you very much, and the floor is yours, Mariane.
Thank you very much. So yeah, I'm going to present you part of my PhD. So when thinking about the impact of the environment on the acoustic communication, we often think about how the signal evolved to propagate in a particular habitat, for example, if it's a closed or an open habitat. And we also think about how it evolves, for example, to avoid being masked by other sounds from other species, for example, like humans. So we study how signal transmission shapes signal structure, but for all the vocal learning species, songs are not only the result of what is heard and what will be heard, but relies on cognitive abilities, on what they learn, how do they learn. And that's what that study is about, the impact of pollution on birdsong learning abilities. So we studied the effect of two kinds of pollution and the effect on learning abilities. So the first pollution we study is air pollution and also noise pollution, with a special focus on air pollution. So why air pollution? Because actually there are several studies on the impact of air pollution on the brain, cognitive abilities and behavior, mostly in human, like for example with an effect of air pollution on depression, like impaired memories, but also in animals in the lab, like rats, like a change in brain structures, or problem with, social interaction impairment. But with birds, we don't have many information about these potential effects, except suboptimal risk-taking behavior, but never related directly to the song learning. However, the air pollution can impact birds' brains and behavior through several pathways. All these things have been shown to have a link between air pollution and the bird's brain. But none of them, to my knowledge, have been linked to bird song learning, except through the HPA axis overstimulation. So basically, the overstimulation with stress hormones that are especially neurotoxic. And birds are potentially sensitive, highly sensitive. They have a highly efficient respiratory system that make them likely to be sensitive to air pollutants. So regarding that mechanism, like the HPA axis overstimulation, there is even a theory based on that, which linking them to bird songs. The name is developmental stress hypothesis and bird song. So this hypothesis postulates that stress early in life can interfere with the ability of birds to learn their songs. And some studies show that, for example, sibling competition, food deprivation, or direct injection of glucocorticoids, so the stress hormones, can interfere with the complexity of the repertoire or the precision of copying songs. But to my knowledge, no one studies this hypothesis with wild animals and directly linked to environmental conditions, and no link also to air pollution as a potential stressor. On the other hand, noise pollution has been more studies on a bird's brain. So for example, like showing song learning impairment, changes in brain structure, immunosuppression, disruption of normal glucocorticoid profiles, and so has been identified as a developmental stressor. So to summarize, we already have links between the brain and cognitive functions and song learning, also with different kind of pollution and the brain or cognitive functions, but no direct link between air pollution and the song learning, and that's this gap that we try to fill with our study. So the main question will be, does pollution impair learning? And as a broader picture, the question will be, what is the relationship between environmental conditions and learning? What happens to culture evolution when there is a learning impairment? So for that study, we will use Great Tit. Probably know that bird already. It's great for this kind of study because they have a short lifespan, a similar exposure of pollution through life, and can be found in both polluted and non-polluted areas. Also, learning accuracy is likely to matter in that species because they do song matching between males to say like, I'm talking to you. And also it looks like there is like a female preference for local song types. So what do they learn? They learn from 2 to 8 song types, it can depend, and yeah, they can have like different song types such as or even. And when do they learn and from whom? So let's take the example of a young bird, or that black bird. Here it's the first spring, and when the Great Tit starts to be territorial again, the young will try to find an available territory and will learn his songs from its neighbors. And so that's why we can find in the Great Tit's geographical pattern, which means that if like 2 birds are really close to each other, they will sound really similar, whereas if they are really far away, they will have like almost no songs in common. And now we can ask, like, how do we study learning in the field when we don't know we have no control on what they are learning, and also how to study cultural evolution without a time machine. So for that, let's imagine like 2 populations. One population is full of high accuracy learners, the other one with a lot of low accuracy learners. After the first generation in the high accuracy learners, it's still orange songs, whereas in the other ones, like, they copied but not that great, so it would be like yellow songs, brown songs, sometimes really completely different songs. And if you repeat that through generation and generations, at the end you will have something like that. With the high accuracy learners population, you will have a high song sharing within the population, also a low song diversity, whereas with low accuracy learners you will have low song sharing within the population and high song diversity. And that's what we expect to find in our population in both in polluted areas and non-polluted areas. So our method, we are going to select sites with different pollution exposure. Then we will record the bird's repertoire, calculate the song sharing within the population, and then inferring this learning accuracy through modeling. So that's why we recorded in 11 sites through the UK and Italy. And here you have a representation of my different sites, because we try to have to go along a gradient of air pollution. So here we use NO2 as a proxy and different level of noise pollution. So for now there are just estimates, like qualitative estimates, but there are like quantitative data in process. So also, sorry, it's still PhD, you know, so I will be able to show you only 9 populations today. And so, yeah, we also try to have cover a broad diversity of urban gradients. So we have like national parks, we have like really urban parks, or we have like rural parks but really close to airport and motorway, for example. So in total, yeah, we recorded 596 birds. And then to calculate the song sharing, so first we measure the song structure with the software, we make the quantitative comparison, and then we assess the diversity of song within the population. So to show you my results, if you remember, there is a geographical variation of these birds, so that's why it's important to plot the song sharing with different categories of distance between birds. So that's the first results. So each line is a population, and so that's why the color represent the proxy of the air pollution, and on the y-axis it's the song sharing. The first thing we can see is that it's decreased with distance, which is like we can find in literature. And also we can see like there is also a bit of a tendency like for low pollution population, so in blue-green, to be higher than in high pollution population. But just like that, you could think that I'm just saying that the song sharing and the learning accuracy are directly related, but of course there are other things to take into account. So in the past, many parameters have been shown to have to be important for this kind of for learning accuracy, and yeah, we have to take them into account for our study, especially, for example, population density. A bit late, so I'm not talking about that, but yeah, we estimated the population density around our population sites to take it into account. And now, so we have an idea of population density, but how could we unravel all these different parameters? By using modeling. So for that, we did the evolution again. So basically, we have the last stage of evolution with our field data and our song similarity in the population. We have theoretical knowledge about how do they learn, the process of the learning, and we have an idea of which parameters are important for this learning. So basically, we create an agent-based model where we basically say create that amount of birds. Here are the rules of the game. I am a bird learning songs. Repeat that for 2,000 years and find the parameters that allows this artificial word to look like our actual field data. So we compared that this simulation with ABC, and once we have like 1,000 simulations that fit our data, we took them and extract these parameters, and the name of these parameters are the posterior distribution. So here you have the plot of the posterior distribution of mutation variance. So basically it's learning accuracy. If it's really high, it's a low learning accuracy. Each violin is a population, and it's plotted against like the NO2 concentration. So what we can see, if we do like a correlation for each of the simulation, it's almost always positive, and with a median of like 0.6. So what we can see is that the higher the NO2 concentration, the less accurate the learning is. And then if we split by noise pollution categories and we subtract with the correlation, it's close to 0, the difference. So we can see that it's not enough to explain the learning accuracy between quiet and noisy sites. So in summary, there is a negative correlation between learning accuracy and air pollution, and noise pollution is not enough to explain that learning impairment. So it might be the first evidence for developmental stress in the wild, and sound learning can be vulnerable to environmental stressors. So it's important to look at the brain, make sure about the mechanism. I'm also aware that it could be an effect of other stressors, such as food urbanization. We can also wonder if it's a honest signal for females to realize, the condition in which that male has been growing. Also, it's important to think that female can also learn like which song is which, so it can be also important for females, and it's important to look at it. And we can think also that it might be plasticity, not only just can be a switch of strategy, for example, switching to more aggression instead of more learning accuracy. So yeah, potentially we can disrupt animal culture, and by me a promising system to get inside of the purpose of song learning. So thanks to my team, and thank you for your attention.
Okay, thank you so much, Mariane. We have time for one small question. If you guys, yeah, maybe, yeah.
So you put a lot of emphasis on learning accuracy. You use it as a proxy. Would you say that it's a positive, a negative, or a neutral phenomenon in Great Tit's population?
A negative or positive thing to be really accurate with your song learning, you mean?
No, like on the population. On the population, would it have a negative effect if there is a greater or lesser learning accuracy?
On the population, if you talk about the population size or something like that, I don't know. And also we chose the Great Tit because it's quite a stable population, you know. So potentially it doesn't matter that well, or it will be important in the really long time scale. It looks like it's important that species, that the learning accuracy, because why we think they learn from the neighbors and why it is important to mediate interaction is because they do song matching, so they sing the same song type that the neighbor is singing at the same time, to say like, I know you are singing, so I'm singing, I'm replying to you. And also females, they have preferences for some songs, so potentially they learn, if they learn the local songs, they would be more likely to have like to mate. Then potentially it won't change at the population level, more the culture of birds. Also maybe it won't be selected as much, and they might switch off mating strategy, something like that.
Okay, so in summary, it may have an impact on the evolutionary processes, but it may be on the long term rather than on the short terms. And you would not say that in 10 years, because there is a higher or lesser learning accuracy, a population of Great Tits would be decimated because they didn't learn the right songs.
Yeah, I mean, it's hard to say. Like, there is no direct thing. It's not like I'm saying that if they don't sing the right songs, a female won't copulate with them, and then they won't have chicks. You know, I mean, I think the population are quite stable for these birds. So yeah, potentially in the really long term. But yeah, it's always this kind of question when there is disruption of the communication. We can. Think that it would be a disruption of population size, but hard to tell.
Thank you.
Welcome.
Okay, thank you very much. Sorry, we are a bit short on time, so feel free to have a coffee with Mariane to discuss about this work. And
thank you, Mariane. Now, please welcome Breatriz Tinoré. She will present assessment of potential impacts of an aquaculture unit in Leros Island Aegean Sea, Greece, on the vocalizations of Tursiops truncatus.
Okay, good morning, everybody. I'm going to present to you the research we conducted on the fish farm of Leros Island, where we aim to assess the potential impacts on the vocalizations of a subgroup of bottlenose dolphins, which frequently forage in the area. So first of all, the rising demand for fish products has led to a rapid worldwide increase of aquaculture activities in the Mediterranean seas. Only Greece is responsible for 40% of the aquaculture production. The main species that they are farming in these aquacultures are the European sea bass and the gill-health sea bream. Fish farms are also known by causing organic enrichment in the sediment, which is produced by releasing of organic and inorganic nitrogen and phosphates, which can typically lead to eutrophication, which basically results in the slowly decrease of oxygen dissolved in the water. Also, the fish farms are also known to aggregate wild fish because of the large quantities of uneaten food that is led by the fish farm units, which this leads to the dolphins to come and do opportunistic feeding around the fish farm units. So our study area was formed by two different locations within the same area. It's located in the East Mediterranean Sea, in the Northeast Aegean Sea, and it comprised different islands such as Samos, Icaria. I'm not going to tell you all the islands. So first of all, the study area between the islands is characterized by shallow waters going around 200 to 600 meters deep in the south, and then in the north we have the oceanographic canyons. We go down to 1,400 meters deep. And then the fish farm, which is located in the north of the island of Leros, which the depths are around from 15 meters up to 80 meters deep, and it comprises of 5 different units. So in order to achieve the aims of the study, we analyzed the data from boat-based surveys near and outside the fish farm. We collected the data from January 2020 until March 2024, and the acoustic data was collected with 2 types of hydrophones, one the tow array hydrophone and another one the broadband hydrophone. So for the analysis of the data, this was a small project. So we analyzed 450 whistles, which 190 were collected near the fish farm units, and 250 were collected far from the fish farm units. What is also interesting to point out is that some of the individuals, so some of the whistles that we have from near the fish farm and outside the fish farm, the whistles come from the same individuals, because the same individuals that often visit the fish farm, they are also foraging in other areas of the study area. So the variables measured for every whistle were delta time, peak frequency, delta frequency, and whistle type. And also for every recording, we note down the presence of burst pulses. And then we did some descriptive statistics of the whistles collected, but also we did a general linear model in order to evaluate the potential influence of the fish farm in the different variables. So the first results shown by the descriptive statistics, it showed that there was not such a big difference between the whistles. As in the mean frequency, the max frequency, there was not such a difference, and you can also see it in the box plots. So that's why we went to the results for the GLM, in which we found that for the best fitting model, the different variables that we picked were the peak frequency, delta time, and the presence of burst pulses. So with this, what we found is that is showing lower peak and delta frequency for the whistles near the fish farm, and also a higher delta time and a higher presence of burst pulses in the recordings collected near the fish farm. All of these results obtained indicated that lower frequencies and longer whistles can be related to trying to mask the vocalizations from the noise pollution created near the fish farm units, created due to all the machinery and all the presence of all the fish there, as well as it can be associated to depredation behavior, which also links with the higher presence of burst pulses, which is also related to feeding behavior. So in this instance, the results suggested a high frequency of opportunistic feeding near the fish farm, which this could lead to weakened social bonds and in return can lead to poor reproductive success in the subgroup that frequently visits the fish farm unit. So for the takeaway message, as we saw, the habitat of the bottlenose dolphin overlaps with aquaculture units in several coastal areas. However, in this specific case, in the Leros fish farm, there was no apparent conflict between the subgroup and the aquaculture unit, as after talking with the people working in the fish farm, there was no damage to the nets or yeah, there was no previous damage to the nets done. Also, the fish farm aquaculture, they are not allowed to put acoustic deterrents in the fish farm units, which in other study areas in the Mediterranean has led to a big damage on the dolphins being there. So further research is needed as well to evaluate the potential impact of eutrophication in the bay, which this can be done by studying the mesobenthic biodiversity, for example, as well as the potential impacts on the social structure of the subgroup in the dolphins. This we have already started it by capture-recapture methods using photo identification, in which we have already identified 40 different individuals which frequently stay in the fish farm. And finally, it's also important to note that clarifying the ecological role played by the fish farms can also help in management plans to reduce the potential impacts on the marine mammal species. So the final goal of this is, after recollecting information on this specific fish farm in Leros Island, we can hopefully communicate with policymakers in order to see, okay, is the fish farm in Leros, can it be as an example of a fish farm that is being sustainable, let's say, towards the dolphins in the area? Is it something that can be improved, etc., etc.? So thank you very much.
Thank you, Breatriz. We have time for 2 or 3 questions. If you want. Yes?
Thank you for the talk. It's very low down. Is it not possible that you're looking at 2 very different behavioral contexts here? When you have feeding dolphins and free-ranging dolphins, could that not potentially alter the vocalizations they're using?
Yeah, so we were also trying to pay attention to compare trolling feeding dolphins outside the fish farm versus the foraging in the fish farm. But also we had different behaviors in the fish farm, not only feeding. We have also seen them traveling. We have also seen them mating, socializing. So we have a variety of different behaviors, both inside for the dolphins near the fish farm and outside the fish farm. So yes, we're trying. This is just the preliminary results, but further, I would like to be able to have more recordings with all the different behaviors, both near the fish farm and outside the fish farm.
Okay, thank you.
Thank you.
Another question? Yes?
You mentioned that you had photo identification, but you're using whistles. Have there been attempts to identify signature whistles so you can use less visual and more audio for saving money purposes?
Yes. So until now, all the data that we were collecting in any case was with boats. So even if we were using the hydrophone, we were using the boats. So that's why we were combining photo identification and acoustics. And yes, this is something that we're just starting for the signature whistles for both the ones outside the fish farm and near the fish farm. And what we are hoping now is also something different for the PhD, is to develop long-term monitoring, but low budget, because I don't have much budget for the PhD. So that's what we're hoping to do, to create the signature whistle catalog right now with the photo ID and acoustic data we have. So later on we can hopefully continue the monitoring only with the device that we're hoping to develop. Yeah.
Awesome.
Thank you.
We have time for 1 more question, if you want. No question? Okay. Thank you, Breatriz. So now, please, welcome Léa Mariton. She will present impacts of forest degradation on understorey Amazonian bird species, the contribution of ecoacoustics to a better understanding of their ecology.
Hello everybody. On the mic, okay. So I'm a postdoc at the French National Museum of Natural History, and today I will present this work on the impacts of forest degradation on understorey bird species. So to begin with, we've been talking a lot lately about the deforestation of the Amazonian forests, and indeed, since a few decades, there have been many incentive and regulatory measures implemented to try to slow it down. And the good news is that though it's still not enough, now we have slower rates of deforestation in some tropical nations. However, one question we are almost never asking ourselves is, what about the remaining forests, the ones that are not anymore at risk of deforestation? And unfortunately, they still suffer from a lot of disturbances. Local ones, like fires, selective logging, but also landscape ones, because the forests are now fragmented. The connectivity is lower, there are strong edge effects, and so on. And so we can wonder, eventually, are those impacts of disturbances that big, I mean, compared to deforestation? And Barlow et al. Tried to answer this question in 2016 by focusing on the state of Pará in Brazil. And they showed that the toll of degradation due to disturbances on biodiversity there was equivalent to the deforestation of a huge area of primary forests. This area being even greater than the effective area deforested in the whole Brazil during 9 years. Also, Beranger et al. Studied in 2018 wood density as a Kaplan trait reflecting the recovery of primary forests after degradation. And they showed that even though the disturbance stops, wood density will increase, but might never reach again the same level as before. Also, by focusing on the wood density of saplings, they showed similarities between disturbed primary forests and secondary ones, which can indicate a worrying process of secondarization. But why is it so important to protect these forests? Among many other reasons, they are amazing biodiversity hotspots. They host, those humid tropical forests hosts about 60% of the global terrestrial vertebrate species. About 30 are endemic to those forests, and about 20% of them are at risk of extinction. However, most of the studies focusing on those disturbances focused on plants, and we have a knowledge gap on what about the impacts on fauna. This is why we chose to study understorey bird species, and more especially 4 species with different functional traits. And today I'll show you the results on Ilopezis witakeri, this one, which has been described in 2012, so it's quite a young species. We basically don't know anything about it, and it's a solitary terrestrial ant-pither. So the first question was, how are we going to monitor this species? Especially because we expected it to be a mobile one with large home range, rare, and we didn't know anything about its activity rhythm. So we needed to acquire a very large data set on large spatial and temporal scales. And you might have seen me coming, but the only solution was passive acoustic monitoring. So my colleagues used Audiomothis in 2022 to carry out a field session on the states of Pará, near Santarém. They monitored 23 transects of primary forests along a forest degradation gradient. There were 2 to 3 sites by transects, and about 2 to 8 mornings recorded by sites. And at the end, we ended up with about 300 mornings of recording, which is amazing, but also a huge quantity of data. It is the equivalent of monitoring the forest for about 56 days in continued without stopping. So I couldn't process it with my tiny own brain. And this is why we chose to use machine and deep learning techniques to try to process this data. We evaluated that we needed about 500 templates of presences of the species and 800 absences to be able to use those kind of methods. The bibliography and preliminary explorations show that the song of this bird is a 4 to 5 syllable one. It is a deep song below 1 kilohertz, so not many birds there. And we chose this template as the reference one. With it, we performed template matching on both our dataset of 2022 and another one recorded in previous years on the same sites because we didn't have enough data. And at this point, we had data for only 4 sites, so the species is indeed quite rare. So with those data, we trained a first convolutional neural network. I won't go deep on how it worked because it's not my specialty, but just so you know, we used as training data the data from the template matching, but also data on 60 other species. We did data augmentation, and the model architecture was a MobileNet V2, and the top layers were 2 fully connected layers separated by a dropout one. So I validated the results of those CNNs for high confidence score, and unfortunately, it was not good enough. So we chose to use those new labelings with the previous one to try to train other CNNs. At this point, we had presence of the species on 6 sites. So we trained 3 other CNNs. The details of these CNNs are here, but what you need to know is that our exploration showed us that the second one was the best. It's just an improvement of the first. The fourth one was not good. I had a lot of detections with high confidence score, and I think it might be due to the fact that it was trained with too much presences compared to absences. This is very unbalanced. And the third one was mixing both songs and calls in the same classes, which might be quite problematic for birds like mine, which has different songs and calls, very different. So for the CNN we chose, I checked all best detections by sites and days. I determined that the species was present in 7 sites, and I checked all the detections above 0.5. I won't go deep into the other analysis, but just so you know, for the activity rhythm, we did estimated density with stratified weights. And for the impacts of forest degradation, we performed generalized linear mixed models on the raw number of detections of the birds or the presence-absence by days and sites. And we used many covariates like precipitation rates, covariates that was reflecting forest degradation, and many characteristics of the primary forests. So I will skip them. We used 2 to 3 random effects, many different laws. And we did dredges to select the best models according to the AICC. So the results were that thanks to our CNN, I could find more than 2,000 true positive detections of my birds on 4 transects, 7 sites, and only 26 days sites, which means that the species is indeed quite rare. Most of the detection were 4-syllable songs compared to the 5-syllable songs that is usually described. It was usually one individual singing for a long time, and sometimes we could see 2 individuals responding each other. And this is quite interesting because, as you can see, the second song is a descending one here, and this is quite different from the one that is usually described. And we hypothesized that it could be, the female song. So about the activity rhythm, we saw that it was very concentrated around sunrise, so it could be very useful for further studies. And then the impact of forest degradation, those results are quite new. They are from last week, so I won't go very deep into them, but just so you know, wood density had a positive impact on the number of detections and presence absences, which could reflect the fact that forest degradation is indeed impacting these birds. For the other results, they are quite hard to explain. I need to discuss it with my colleagues, but for example, maybe the amount of primary forest is impacting negatively because birds are concentrating in the remaining forests when they are. And maybe richness is accounting for a lot of pioneer species, so it is to explore. So as a conclusion, I've seen many questions I'd like to answer. On the ecological side, I'd like to know the results on my other birds, which has more complex sounds. I'd like to know more about the activity rhythm around the day, around the year, what happened in secondary forests. Can we disentangle the impacts of the different disturbances? And on the acoustic method sides, I have many questions. Is my CNN generalizable to other places, other years? I'm not sure about it, to be honest. How to improve it to have much less labels work, because it's still a lot of work. Maybe using my new labels, using new recordings from my colleagues. With which bird my species are mistaken for. And I noticed that you could hear selective logging in the recordings. They are very distinctive. There is very distinctive sounds, and so maybe it could be good to try to learn to detect it to better account for it. So, thank you for your attention.
Thank you, Léa. We have time for a few questions, if you have. Yes? Oh.
I was wondering if you know if there is a correlation between wood density and the other variables like primary forest and the other variables that you looked at.
You mean if there is a documented link, or if I found one? Sorry.
Sorry, if they are correlated, like if you know, like more dense areas tend to be primary forest or things like that. I don't know.
About the density of the forest, no. This is wind density that is a quite good, I think, proxy of the amount of degradation of the forests. And I studied only primary forest, but in secondary forest, wood density would be lower. So I think it's the best I can have. But I tested many others metrics to try to characterize forests, and the others I had no response of my birds. So distance from edges, the amount of forest, these kind of things. Okay. But one thing that has to be said is that as I had only data on 26 sites, my statistical power is quite low. So.
Mm-hmm. Yeah, but very cool study.
Thanks.
Yes.
Hi, thank you. That was really interesting. So I know in lots of primate species, it's not actually the size of the patch of rainforest that's left, but it's more the amount of mosaic of different forest types within the patch that affects the changes in their vocalizing behavior. So I just wondered if you had any plans to kind of look into that as well, and whether that's affecting the vocalizations of these birds.
So I didn't study directly the vocalization behavior. This is just a number of vocalization, but I wondered if it could be an explanation for the fact that the area of primary forest had a negative impact, because we don't know a lot of things about these birds, but I usually read that it loves gaps, tree gaps. So maybe when there are hedge effects, it would favorize this kind of things, and maybe favorize my birds. I don't know, but this is one possible explanation.
That's cool, thank you.
There is other questions?
Question? Okay, cool. It's time for coffee. So the coffee break will be in the room next door. It's going to be a bit longer than planned because we are a bit too early, but it's for the best, I guess. Let's be back at 10:40 for a start at 10:45, please. Enjoy the coffee.
Should I start again, or? No, it's okay. Yeah. I hope that the sound is fixed now. Sorry about that. So I'm going to talk on this slide about contrastive learning. I'm going to show two methods, one that is self-supervised and one that is supervised, that leverage the labels. Okay. So for the self-supervised method, suppose you have a batch of data, and you can select one data point. You call it an anchor, depicted by the first image with the dog. And you can create another view from it using data transformation. Here, for simplicity, it's a crop. And you tell your model, I want the anchor and the positive to be close to each other in the space of the model. So the space is depicted by the hypersphere. And any other examples in the data is called negative, so you push it apart from the anchor. You have another dog that it is considered a negative, but you don't have the label, so you cannot say whether it's positive, so you consider it a negative. And the extension of this model using labels, you can consider the label. So you can have more positive for the anchor. So you know that there are two dogs. They come from the same label. So you also include them to be pulled together in the embedding space. I'm going to talk quickly about two other methods for self-supervision. They differ from the previous one, where the regularization was to push apart different examples. Here, suppose we maximize similarity, which is the regular first criterion. For the second one, we want to actually decorrelate the variables of the feature pairs, and that way you can learn a feature that is informative, and you don't have redundancy in the variables of the feature vector. Now we're done training. Let's do evaluation with few-shot learning. So in few-shot learning, either for validation or test, we consider k-way n-shot tasks, and suppose you have a pool of your data. You sample k classes, and from each of the classes, you sample n example. So suppose you sample this small pool, so you have two classes and two examples per class, so two-way, two-shot. You call this a support set, and you use the label to adapt your model or train on it, so you only train on two examples for a two-class classification problem. And then you sample another set that is called query set. This is the set that you will do your prediction on, and then you will evaluate your model. Since you figured already this is done randomly, so you have to do this multiple times in order to reduce the effect of randomness. So now you have a pre-trained neural network on your training. Either you have data labeled or unlabeled, and you have your support set. You can do a simple method that we're using here, so you can just project your images, compute to the feature vector from your neural network. And if your model has been trained well, so it will put together the similar examples close to each other. You have a query set, you compute its feature vector, and you can simply just compute the distances and make the decision based on which is the example the closest in the support set, and assign the same label. So this way you can measure the capability of generalization of your pre-trained neural network. Just a quick reminder, in the training set you had different classes than the ones that we see here. For experiments, so we use this data set called Berkeley 2020. A pruned version of it, for simplicity, it's used in the meta-audio paper. It's a benchmark for audio few-shot classification. And what they do in the pruned version, they remove examples longer than 3 minutes, so they keep the audio files pretty short. So how do we do the self-supervision training? So suppose you have your audio file that is maybe 3 minutes long. You can select a window to do your training on, so it can be random. And then you compute maybe time frequency representation, mil spectrogram, and what kind of views you have to do. In images we see you can do crops, but in audio, what do we have to do? For birds in particular, so we need domain knowledge. So we ask ourselves, can we just ignore the domain knowledge and use something domain agnostic? And this is what we do. So we use time shift of the mass spectrogram. So we shift it on the right and on the left. It will still preserve the semantic of the audio. We mask some frequency bands, so to distort the two views. So they are different, very random masking. And then we can maybe mix it with some random noise or background so that the model can focus on the foreground. And you maximize the similarity, and you can use any model that you like or any neural architecture. So for experiments, this is a 5-way one-shot, so it's a 5-class classification problem with only one example per class. And the first 5 rows are the baselines from the paper, and the subcon is our supervised baseline that we use for reference. We can see that our model performs well even in the supervised case. And for self-supervision, we use the 3 models that I described earlier, and this is the results that we get. And for reference, we use an audio model that is known called PAN. It's pre-trained audio neural network that has been trained on a general-purpose audio dataset. And we can see from it that yet our model learned some informative features compared to the CNN14. But we can see that there is a big gap between the self-supervision and the supervised baselines. And our assumption is that maybe because we use the random window selection, maybe that's why our model is not performing well in this scenario. So we, instead of doing random selection, we maybe say, let's use a weak classifier that can maybe classify bird from background. And that way we have a smarter choice of the window that we can select. We do this on the supervised baseline, either on training or on test as well, and we can see a small improvement in performance. And for the self-supervised models, we can see that there is a big improvement in performance up to 20%. So it improves both on the self-supervision and the supervised methods. And similarly, the contrastive method seems to be the one benefiting the most from it. As a conclusion, so we show that self-supervision can learn meaningful bird representations from sounds using only data without labels. And selection of which segments you use for self-supervision is crucial, and maybe using simple solution like a quick classifier can actually work, and it's very effective. And if you're interested, we have published this paper recently, and this is the title, Self-Supervision for Future Bird Sound Classification. And thank you for your attention.
Okay, thank you, Ilyass. Does anyone have a question? We have time for 2 questions, I guess. Yeah.
Hello, thank you for your presentation.
Thank you.
I don't know if I missed it, but I was wondering, how did you check on the invariance of your representation, except for accuracy? Is there, do you know a way to do that, and did you do it?
Okay, this is a really interesting question. So one way you can do that, you can verify if your feature vector represents different information by computing correlation between the variables representing your feature vector. That way you can know if it's informative or not. But other than that, you need some labels to compute maybe similarity between examples coming from the same class, and see if you have like maybe clustering behavior that you have a pattern in the embedding space. And I think that this is actually an open research question. It's still ongoing, and some people maybe use the rank of the embedding matrix and do some stuff like that. But yeah, still open question.
Thank you.
Thank you. I don't have a clear answer to that yet. Thanks.
Okay, another question maybe? Okay, maybe I have one question.
Yes, please.
How can you ensure with your like cropping in your when you do augmentation and you crop randomly the data? How can you be sure not with span like
the random one?
Before year.
Here, yeah.
When you do the time shift, how can you ensure that you're not shifting the content actually towards the edge and out of your spectrogram?
Yeah, this is a good question. So we don't have a constraint about that. But one thing that we do for sure is that we do circular shifting. So if you shift to the right or to the left, like you still have the audio from the other side, it still doesn't make sense because you have like maybe the end of the sound and then you have the beginning of it. But empirically it worked. But yeah, we don't have a constraint about that.
Okay. Thank you.
Yeah.
Maybe it's a follow-up question as well. Do you put any constraint in the spec augment to not mask the signal itself?
Yeah, this is a good question. So actually, we mask maximum three bands, and we limit the size of the band
Okay.
So that in order...
Is it random? Both,
yeah,
both the size?
Yeah, both the size and the number are random, but
okay,
there is an upper limit, so we don't destroy the signal. We tried different values, but I think this is more going to be experimentally different from data set to another, and try what works
Do you
best.
also do the time warping part of the spec augment, or just the masking?
Just the masking. We've tried to do the time warping, but actually it doesn't work. It kind of destroys the information.
That's my experience as well.
Yeah, with bird sounds, right?
Well, with just bioacoustics in general, not just the birds.
In my case, I was like the performance was dropping the longer you train, so I suspected that some species are close to each other if you do the stretch, and maybe that would confuse the model.
That makes sense. Thanks.
Thank you so much.
Okay. Thank you again, Ilyass.
Thank you.
If anyone, no. And I guess we can now welcome Bruno. Good transition, I guess.
All planned. Sorry? All planned.
This is still your title? Is still the same?
No, I changed, but
okay.
Yeah, it's okay.
And so, thank you, Bruno, and we are you from fin whale detection to synthetic vocalization generation using GANs. You have 15 minutes.
Yep. All right, thank you. Thanks to the organizers for organizing this event. So I'm Bruno Padovese. I'm a postdoc at Simon Fraser University in Canada, British Columbia. And in my presentation, I'll be covering quite a few topics, so it's not really a deep dive on one particular aspect of deep learning, but more a wide breadth of projects that we have been working on back in Canada. So yeah, basically our project, we have 3 goals. First one is to develop a fin whale classifier. This is just a prototype classifier using mostly off-the-shelf neural network architectures and also audio representations. I'm also going to go a little bit into some fun stuff with deep generative methods for creating synthetic data. And all this will be tied together into the project that we are working on back at BC called the HALO project, which stands for Humans and Algorithms Listening for Orcas. We have a website as well, you can check it out. So we're a pretty sizable team, multi-institutional. We have collaborators from the US, from other provinces in Canada. We're multidisciplinary. As you can see, we have marine bioacousticians, data scientists, deep learning researchers like myself, data managers, software developers, system administrators that are actually building a platform. And what we're working on is a whale forecast system. So we're trying to predict not only detecting a whale, but where they're going to be in 1, 2, 3, 4 hours. Why? Well, it's because we want to warn incoming ships to the presence of these whales. So this will serve government institutions, the port, and some of our collaborators into predicting where these whales are going to be so that they can take the measure necessary. And we have essentially 6 targeted species. Most of them are killer whales, different subspecies of killer whales. And this is the main actual focus of the project, as you can tell by the name, well. But we also have a couple of other species that are also found in the region. Those are humpback whales, gray whales, and the species that I built the classifier for, fin whales. So this is a general pipeline, deep learning pipeline for detecting marine mammals, or I guess you can even apply it to other terrestrial bioacoustics, which is essentially we have the waveform. Although you can use the waveform directly to train a neural network, it's more commonly accepted to transform this into a spectrogram representation. But I also want to clarify that that's not the only representation that you can go for. It could be a magnitude spectrogram, Mel spectrogram. Maybe you could also choose to do something with wavelets, or even co-similarity matrices. So essentially, it's transforming the data from 1D to 2D. Why? Again, for the convenience of using the powerful deep neural networks that were developed for images, so we can essentially treat the audio the same way. And this is pretty standard in the field. And at the end, we're going to get an output which is essentially saying either which whale or which animal the sound was from, if it's a multi-class classifier, or a binary detector, which will simply tell it's a whale, it's not a whale. For this project, I used a data set from the Antarctica. I know some of you have also worked with this data set, but it's essentially a blue and fin whale data set collected from several points in the Antarctica. For this prototype, I decided to use just one location, separated into 2 years. 1 year for training, another year for testing the model. And as you can see, you have not only a label for the blue and fin whales, but also the different ecotypes and vocalizations. So one important consideration when building these classifiers is which representation you're going to go for. And even once you choose, you have several decisions to make. If you're doing a spectrogram, what's going to be your time window? So how many seconds are you actually going to show the neural network, not only to train, but then later to decide if the clip that you're showing it is a whale or not a whale. At first, I used the representation that a colleague of mine, Romina German, used for her blue whale detector. She was trying to classify blue whale calls into R calls, D calls, or, well, background noise. And she got pretty good results, which are these pie charts here. And she was using a 10-second window for the spectrogram. And this made sense because it's more or less around some of the blue whale calls are that long. So I tried to use the same spectral representation, which worked okay. It's the results on the top. But one characteristic of the fin whale calls is that they are much shorter than some of the blue whale calls. So I decided, okay, can I change the scope of the project to, instead of building a multi-class classifier between fin whales, blue whales, and just background, just make it a binary classifier of fin whales and not a fin whale. And this way, I also decided to reduce the spectrogram size to 3 seconds. So just this simple, simple approach towards building the model, and it already improved the results quite a bit. And again, this is using a very simple neural network called residual network. So one question is, is there perhaps a general spectral representation that we can use that would be good not only for these 2 species, but perhaps other marine mammals that would work well in any problem? And another open question is, well, okay, I trained this model, it works good in the Antarctica. How can I bring it to the North Pacific? which has a completely different soundscape. And in fact, if I try to use this model over there, it's not going to give me any good results. So how can we leverage the data that I have from the Antarctica to use it to detect fin whales in other parts of the world? One way is using transfer learning, which is essentially the technique where we have a model that was trained on one task for one location and use the same model to a different location. Another task, and this is mostly have been my research during my postdoc, is using these deep generative models to augment the data set. And this really targets the root of the problem, which is these neural networks are data hungry. They need a lot of data. So in the last presentation, you saw some simple data augmentation methods like spec augment, and they work really well. But can we use these neural networks that you've probably seen in the media to generate very realistic images of vocalizations and use those to train another neural network? So essentially using a neural network to generate data for another one. And as you can see, I got some really good results. These are killer whale calls, by the way. And they look really realistic. So does this work well to train a neural network? The answer is no. If I give this to a neural network, it will easily be able to tell apart both. And even though it looks good to our eyes, if I generate the stats for both of these sets, they're probably going to look really different. So the distribution between these two different types of data is really big. And perhaps one of the reasons is because I'm generating not only the vocalization, but also the background. So maybe we could change this a little bit and instead just generate the synthetic vocalization without any background and use actual real background to create an embedded synthetic vocalization. So we're using both synthetic data and real data to compose our data set. We could even use, get fancy here, use multiple generative models to get the data, but essentially that's the idea. I haven't applied it yet, but I'm hopeful that this will go well. So just to conclude, deep learning can do a lot of stuff. I actually recommend everyone to try it out. It's not that hard to get an off-the-shelf network working, but can aid the detection of endangered species, improve the model performance through data augmentation, self-supervised learning, be used for multi or binary classification, and I think it's also important to make ready-to-use software. All the models that we're building for the project are going to be open source, and hopefully we're actually going to build some good tutorials and tools for the community to use, and make, of course, everything open source, ideally. And that's about it.
Thank you, Bruno. So does anyone have a question? We have time to have one or two quick questions. Yes, Ilyass.
Thank you for the interesting talk. I have a question about transfer learning. Did you use one location to train on and transfer to one location, or you had multiple locations during the training?
So in particularly that I used only one location to transfer it to another. But in the full version, I would have multiple locations and then use it to transfer it to a completely different location, which is basically essentially several points in the Pacific, in the Antarctica, and then transfer it to the North Pacific.
Okay, actually this is a really good setting because there is a literature called domain generalization, and if you have multiple sources, you can maybe make the model robust or to ignore the domain information and only to retain important information that you will transfer. So yeah.
Yeah, that's essentially what we really want to do. We usually have very good success with transfer learning, and not only transfer learning from one location to another, but perhaps from a completely different domain, like images. Use a model that was trained on the ImageNet data set to use it on audio data that also works often quite well.
Thank you so much.
Yeah.
Thank you very much. Maybe if si c'est rapide. Okay. Well. Okay. En ligne, il n'y a pas de questions. Okay. Thank you. Thank you, Bruno. Then.
Yeah.
And now we can welcome Lucie Jean-Labady. And you can applause you again. You're right. And so we'll welcome Lucie with the presentation. A little bird told me, transfer learning for underwater bioacoustics and passive acoustic monitoring.
Okay, so hi everyone, I'm Lucie, I'm an intern, and today I will be presenting my work on transfer learning for underwater bioacoustics. So for a long time we thought the sea was quite silent, but as you can understand, it's really not. There are a lot of sounds in the sea, and three main sources, which are like biophony, geophony, and anthropophony. My work focuses on biophony, but yeah, the good way to study those sounds are passive acoustic monitoring. It's a great method because it's non-invasive. It doesn't necessarily require human intervention, so it's long-term. It can be done in extreme conditions. But there are also downfalls. The data collected are has generally very low SNR. As you can see on the spectrograms here, the signals can get mixed into the noise, and it's like beautiful spectrograms that we have. Most of them don't look like that. The signal is really invisible. There is also a wide variety of signals of interest. There are like wide frequency and time range coverage. For one sound source, we can have like a wide vocal repertoire. So as you can see on the picture, it's for one species, which is blue whale. You can have like dead calls or decalls. Yeah. On this recording, there are like the decals in the background and the downsweeps in the foreground, but there are like the two signals for one species. So that's for the recording part, and for the signal processing and information processing part, we have noisy labels due to inter and outer viability. Some studies found that the disagreement between experts can reach like 40%. And more generally, the robust annotation are really expensive to get because it costs time and energy. Because as I said, it's like it can be in the long term. So we have like hours and hours and hours of data, and then we need someone to annotate it. So that's why we began to use deep learning techniques. As you can see on the graph, the deep learning models kind of outperform classical physics models. So far, but yeah, but the deep learning still requires robust and high quality annotations to work. So one way to get around this problem is the use of transfer learning. So the late speaker talked about it a bit, but the idea of transfer learning is to use a pre-trained model. You can picture deep learning as a child that have to tidy up his room. But he has no drawers, so he had to design and put in place the drawers himself. And yeah, he had a lot of objects, and then he had to make groups of them to tidy up the thing. In our case, the pre-trained model learns acoustic features. We don't know exactly which, but it's how it tidy up the inputs data. And then once it's pre-trained on some data, we can use what we call the latent space, which is kind of the tidy up room, to put some new objects in, and then try to see if it's also capable of sorting our input data. So that's the principle of transfer learning, and we often add some custom final layers, like just a decision head, which is often like a multi-layer perceptron, or we can also fine-tune the last layers of the pre-trained model to make sure it fits more with our data. So in my case, I use a pre-trained model perch, which was presented in a paper in 2023. It was trained on Xenocanto, which is a large dataset of bird songs. It had like 500K samples, 500K samples, sorry, and the wide species and geographical coverage. And the reason why we use it is because the Xenocanto is way larger than what we can obtain from underwater passive acoustic monitoring. Our data is an open access dataset compiled by Miller in 2021, and I mainly focused on blue whale and phi whale, and as you can see, it's in the southern hemisphere. And in total, we have like 2,000 annotated hours from the 11 site years you can see on the map. And I gave them raw to the pre-trained model. The only pre-processing I did was to chunk the audio in chunks of 2,099 and 6,040 seconds. The first thing I did after the trainings was to plot like a Disney. This is kind of a visualization of the latent space. So on your right, you have like the raw audio in a kind of a messy cycle, and on your left, you have the Disney for the encoded audio. So I just gave the audio to the encoder, and then I visualize the latent space. It's a dimension reduction technique, because like the latent space was in dimension more than 1,000, and then you have like dots in dimension 2. So it's still kind of messy, but you can see that some points are doing very well to be separated from the other. It's especially the case for fin whale calls that are in pink and in brown. Yeah, you can see that some groups are kind of being separated, but it's still very, very messy. And from this, I trained MLP to really separate into 3 classes. And then I plot precision recall curves. For the 15-second extracts, it kind of worked well. For the best score, we had decals like 0707 in precision and recall. So it's really cool. It was only tested on 1 dataset so far, but my work is to test it on the whole Miller datasets. For the 2,200 and 99-second extracts, the performance is quite good, but the curves are looking kind of funny. So we have to analyze it further. And for the extract at 640, the curves are really, really weird. So we have to analyze why and to be sure what it's done. Okay, sorry, I will take from here. You can see that the results are kind of good, but to be clear, the perfect PR curves is kind of a square from 1 to 1. So we are not here yet, and one reason maybe is that we are facing a domain shift case, because Xenocanto is made of bird songs, so bird songs mainly range between 1 kilohertz and 8 kilohertz, whereas for our vocalization, we are like from 15 to 120 hertz, so we have what we call the frequency shift, and it may explain the gap between the results, because the pre-trained model was trained on mid-frequency range, whereas our data are low frequency. So to tackle these issues, there are a lot of future works to do. One could be to fine-tune the last layers of the pre-trained model to make sure it fits with our low-frequency data. Another work that can be done is unsupervised domain adaptation, where we try to match the data from the pre-trained, when we try to match the distribution of the data of the pre-trained model to our data. It's made with adversarial training. And the last thing I have to do is a comparison to the state of the art, because we have a benchmark that was published like 2 months ago, and I want to be able to compare my results to the one that were published. So yeah, that are the future of my work. And thank you for your attention.
Thank you, Lucie. So does anyone have questions? We have time for 2 or 3 questions, I guess. No? Yeah. Please come, Félix.
Thank you for your very interesting presentation. My question is, it seems that convolutional neural networks are invariant in translation.
Yeah.
So why do you think that the fact that the song of the whale are low frequencies, it's a problem for the model when it learned pattern in higher frequencies, when actually in CNN?
Yeah, okay. The thing is, the pre-trained model has a fixed input size, so I had to deal with my sample rate to match the input size. And so, for example, for the 15 seconds extracts, I had a sample rate of like 1 kilohertz, which is kind of weird for the low frequency vocalizations. So basically my signals was like some signals at the bottom of the, if you had to make it a spectrogram, you would see like the signals at the bottom and nothing at the top. So I don't know if the model was trained this way. And another thing is like I think the shift that is easy to make is time shifts, but frequency shift, like just taking the frequency and making it higher requires time compression. So it's also a future I will maybe explore, but I know like the ecologists will be very mad at me for doing so. So I'm not sure.
Okay. Does anyone have another question? No. Yeah, so I had just one question, sorry.
Sorry.
Why did you use, new to bioacoustics, so why did you use these chunks in times like 15, 299s and...
15 was because it's the chunks of the benchmark. So to be able to compare my results to the benchmark, I wanted to do the same thing that they do. And then it's also a question of sampling rate. I was like, I'm sampling my data to 1 kilohertz and it makes no sense, so I'm trying to extend the time range. 299 is the maximal time for like the shortest extracts from the dataset is of this time is 2099, and then to match my initial sample rate, which is normally 250. I also did the 640 seconds chunks.
Okay, well, thank you very much. Well, thank you. And I guess we can now welcome Félix Michaud. And so we will hear from Félix the Achilles heel of bird sound classification, a case study, the Boreal Owl.
Rockstar. Hello everyone, I'm Félix Michaud. I'm a PhD student supervised by Jérôme Sueur and Sylvain Aupert at the National Museum of Natural History. And today I would like to tell you about a story. It's the story of me failing my research and how from failure I finally finished by working on what I humbly called the Achilles heel of bird sound classification. And I'm gonna explain it to you through the case study of the Boreal Owl. And it's very interesting because I presented these results last year at the same conference, and these results were false. And I discovered it 2 months later, and I'm gonna tell you how much I struggled. So, the setup. We installed 4 microphones in a Jura forest to study the soundscapes in relation to climate change. And so you can see the microphones are the yellow dots, And the people from the park were interested in the Boreal Owl because it's a pretty species of interest. And so the Boreal Owl in the giraffe forest. The question was, can we monitor the Boreal Owl from the recording we have? We recorded from 2018 until today, 1 minute every 15 minutes. And it's a pretty interesting case because we know that we had a rodent population peak in 2021, and in the literature they're saying that you can have a peak of vocal activity of the Boreal Owl at this moment and a peak of reproduction also of activity. But how are we going to monitor the Boreal Owl with these recordings? We want to know when they sing. To do so, I developed an algorithm to detect the sound. I started from a dataset of the 6 years of audio. We asked a researcher to annotate this song. We took 2,600 files, and the annotator said, oh, there is a Boreal Owl song there is no, there is not, etc. What happened is that I divided the 2,600 files into 5 seconds audio. From there we got only 1,658 samples with Boreal Owl song and 30,000 negative sample. So here are the trouble starting. I did a random split and I trained on almost 80% of the data and tested on the rest. That's not very, and this is, and to show you my workflow, I take these 5 seconds spectrograms, put it into a convolutional neural network. I really like this picture because you can see what is actually happening in there. And at the end, the program is outputting a value between 0 and 1. Say close to 0, it's absence, close to 1, it's presence. And we have to decide, above 0.5, we have, or it's a song, it's a Boreal song, or above 1.7. It's called the threshold. And this value between 0 and 1 is called the confidence score. I did that. I presented results last year, and I discovered a few months later a mistake in my workflow. So I corrected the mistakes, and what happened was that I completely, everything failed. And I think I spent 6 months not understanding what was happening because the model couldn't fit the data. It was terrible. I tried many methods, new architectures, new loss functions. I did everything focusing on the model, thinking, okay, maybe the problem is I didn't code properly, I didn't do the correct mathematical things. But then I thought, maybe I should take a look at the data. It seems obvious, but it's not a reflex in the deep learning community, not to me. What happened is very interesting, is that I looked at the spectrogram, and here is a nice, pretty Boreal Owl song. Well, the prettiest I could get. And here, where we can barely see the songs, it represents, the number 1 and 2 represent 2/3 of my data. And now I understood what happened is probably during the random split that I did, I maybe trained only on the nice songs, and when I was testing on the really hard examples. So what happened is that I said, okay, and what we can see here is that actually the energy of the song of the Boreal Owl is not very high compared to the energy of the noise. We call it signal-to-noise ratio. We can measure it, and that's what I did with my songs. This is a small image of the distribution of the SNR, we call it. And this is how I discovered it represents 2/3 of my data. So from there, I thought, okay, I'm going to make the hypothesis that the most variation in my data is the SNR. So I'm gonna keep the distribution of the SNR in the training, in the validation, and in the test. And so I did another split of the data, trying to keep this distribution, and it worked, despite the very small amount of data. And then we thought, hey, why don't we study the consequences of SNR in the training data? And that's what we did. So I designed a special, very small CNN. It's only 6,000 weights. Comparison to Burnett, it's 100 times, something like this, smaller. And only one class, which is presence of or absence of the Boreal Owl. And from there, I divided the training data set into 3 sets. Only high SNR, high and medium, and high and medium and low. And I trained this model only with the high SNR. I trained another model, high SNR plus medium. I trained a model, okay. It's kind of complicated, so I'm trying to take it step by step. And here is a part of the figure we obtained. So in green, it's the representation of the result we obtained measured by the area under the precision recall curve. And we can see that the model trained only on high SNR is performing quite well on high SNR. However, on medium SNR, it's very low. On low SNR, super bad. And all SNR, so usually people don't look at that. So you don't know how your model is performing depending on the SNR. And if you only look at this, it doesn't show this. So I really like this graph. And we can compare it to the model trained on high and medium and high to low SNR. And we can see that the models training on medium and low are actually better on medium SNR. What is very interesting is that the Burnett model here, that little arrow, is actually performing on this specific species as much as the model trained only on high SNR. And we can, my hypothesis on that is that this model was trained only on the Xenocanto dataset, which and the song in Xenocanto have a very high SNR despite data augmentation. Finally, this is the model in blue trained on the whole dataset, not only the 384 sounds. And we can see that actually didn't quite improve that much. So there is way more to say about that, but I will go further. Finally, we wanted to compare our model. Here are the specificities of that model with Burnett. And here we can see that we have two very different workflows. We have here, our model is very small, 16 embedding dimension. Here we have 1024 embedding dimension. We have only one class. They have 6,000 classes. They were trained, Burnett was trained on 10 million sounds. We trained on 2,000. However, I found I find a similarity in their response to SNR. And this is, to me, the most interesting results, is that here, I plotted the SNR in the x-axis, and on the y-axis, it's the confidence score, so it's the value between 0 and 1 of the model, and we can see that below 4 or 3 dB of SNR, both our very small model and Burnett are struggling. Despite the training data, despite the size of the models, despite all these differences in workflows, I found the same problem. And I really like these results. I'm really excited by these results. Finally, as a sum up, if you have to remember something from this presentation, the SNR distribution of your data is very important when you are doing the split of your data. Because you sometimes, if you do a random split, you don't test on the things you trained. So please measure your SNRs. The model trained only on high SNR had the same performance in Burnett, despite the difference in workflow. Finally, maybe the last experiment showed a sort of mathematical limit in convolutional neural networks architecture due to the differences in architectures, but differences in workflows, but similarities in architectures. Thank you.
Thank you, Félix. Yeah, so first, does anyone have a question? Yeah, here.
I'm ready.
To be able to measure SNR is to be able to compute it. How did you do?
How I did it? I did it manually, and I went through all the positive examples, and I drew a window around the positive samples, and then I drew a window around stationary noise in the same sample, and then I applied the GB difference.
Okay, thank you.
Thank you. Did you try some denoising method to maybe increase your performances on the test set?
Yes, I did. And this is the result I'm showing, even though I'm not presenting. I tried the PCEN, which is specially made for that, and still the model is struggling. I also tried data augmentation, and data augmentation didn't brought any improvement on the model.
Okay, thank you.
Okay, no question left? Okay, so thank you again, Félix.
Thank you.
And so now we will welcome Yann. Yann B. Okay. So we don't welcome Yann. Okay.
Oui, tout en acoustique. Je vais laisser Gabriel, c'est lui qui est en contact avec Camille.
This will be a presentation of Yann Bale in video. He is the CEO of Ripples, which are sponsor of the JJBA, so thanks to them. And he will talk about their work, especially on coral reef and preservation using deep learning and passive acoustic monitoring.
Good morning, everyone. I'm Yann Bale from Ripples, and I would like to introduce what my team and I have the amazing privilege to listen to every day. This is the Bioacoustic Days, so let's hear what marvelous sound we have recorded with Ripples so far. But how did we get there? So first, who am I? I'm coming from a French overseas territory in the Indian Ocean called Réunion Island. I'm a musician and a diver, and I have an engineering degree in sound processing and a PhD in artificial intelligence applied to music playlist generation. I had some experience in the industry in a research and development department where, amongst other things, I use some recurrent neural networks to modify the sound in real time for guitarists. Since 2022, I'm the CTO and co-founder of RiffPulse, where we monitor coral reefs. What is the problem we are addressing with RiffPulse? It's that there are more than 1 billion people currently depending on coral reefs for fishing or tourism, for example, and 90% of coral reefs could disappear in 26 years. So there is an urgency to act now. Here is some more context and key numbers. 30% of MPAs should be protected in 6 years according to a global agreement. France possesses 10% of coral reefs worldwide and thus has a huge responsibility in their conservation. More than $30 billion could also be lost annually and globally to the decline of global reefs. And one of the United Nations' goals is to conserve the sea using the best available scientific information. But as you know, we don't know much about it. So there is a real need for a better understanding of our seas and their inhabitants. That's why the goal of RiffPulse is to leverage passive acoustic monitoring to gather insights on coral reef soundscapes and suggest appropriate guidance to stakeholders of MPAs. So, we are using standard devices on all our monitoring sites, as you can see on the picture on the left, which displays an hydrophone at 1 meter above the seafloor. We set up continuous recording and have recorded more than 5 million minutes so far on more than 140 sites. We analyze the recordings with bioacoustics and ecoacoustics methods and propose some management actions. 2 examples of what we can give to stakeholders are a speed decrease of boats to respect no threshold to preserve marine life, but we also suggest to set up or postpone fishing restriction dates and zone depending on acoustic activities of key marine species. We provide our clients a dashboard with a map to have quick access and relevant information in color there for each site, such as global ecosystem health or boat presence. We also have this map view where we can give key acoustic metrics for a given site and get long-term trends. Here we can see the average sound pressure level variation per day for 3 months following a pattern based on lunar cycles. I found beautiful that we can have a glimpse at underwater acoustic life. If we zoom in at the day level, we can see the sound pressure level variation per minute during 2 days following a pattern based on diurnal cycles with higher levels during the night. By comparing different ecoacoustic metrics for different sites at different moments, we can infer some information for marine protected areas stakeholders. Now, apart from this ecoacoustics approach, I would like to focus on machine learning for bioacoustics and give feedbacks on some good practices that some of you might know, but since it's emerging bioacoustician days, I wanted to share some topics that I found were the more under-addressed. The first thing is having baselines. If you got a random model that have 100% accuracy, you might have an issue in your toolchain. A random classifier is also good to check the impact of imbalance in classes. A simple MFCC plus XGBoost classifier can give you a simple and quick baseline. Do I need something better than this accuracy? If the goal is to work on a new paradigm or new algorithm, then the answer is yes. But sometimes classification is not the end. The analysis of the presence of some species is. If improving the accuracy is the end goal, then from this baseline and the state-of-the-art off-the-shelf algorithms, you can evaluate a compromise between the time it will take to code and train a new fancy model and the percentage of accuracy you can improve upon. A simple and quick baseline can also help you gather quickly more sound events you can check on and add back to your train set in a semi-automatic approach, and then optimize the hyperparameters and checking the parameter front and so on. I also would like to emphasize the data augmentation part, which is tremendously underused. There are multiple data augmentation methods and tools you can use to help your algorithm train better and perform better on unseen datasets. Once you've got an algorithm running, you better take care of horses. So it's a concept where an algorithm pretends to be capable of something, but in fact is not. For example, you've got a good model for distinguishing between two birds, but once you test it on your data, you got bad detections. It's because in your train set, all the recordings for one bird contains wind, and the recordings for the second bird does not. Congratulations, you made a wind detector. This is an obvious example, but a horse can come from more complex situations, like an electronic bug or interferences, or differences between microphone calibrations. And most of the time when you work with off-the-shelf neural network models, they will require an image as input. I would like to underline 6 differences between a picture and a spectrogram. The first one concerns the dimensions. An image has a width and height and 3 channels for the red, green, and blue colors, while a spectrogram has a time axis and a frequency axis. The second one concerns the meaning of a pixel. For an image, the RGB are 3 channels that depict the intensity of a given color between 0 and 1. For a spectrogram, a pixel represents the amplitude measured in a frequency band at a given moment. This amplitude is computed with a fast Fourier transform. By the way, we are discarding in a spectrogram the phase information, which is like half of the InfIFT information. Moreover, we may need more information in the lower frequencies, and wavelet approaches instead of FFT proves more than sometimes to be useful. Anyway, I've seen multiple times people just taking spectrograms and the best image models and using it as inputs and benchmarking that. Okay, that's a great start, but most of the side of the neural network is used for 2 extra channels for nothing and consume precious time to be trained and precious electricity that is costly and often doesn't come from like renewable energy. The third one concerns the meaning of the X and Y axes. For an image, you can use data augmentation with a rotation and still recognize the cone on its back. But with a spectrogram, if you rotate or tilt by 30 degrees, it transforms a stationary frequency sound into an upward sounds, which are not the same. The fourth one concerns the transparency and opacity. For a given pixel, in a bioacoustic spectrogram, you may have multiple sources producing sound at the same time and in the same frequency band, so it adds up. You cannot know which is which and who is who. In an image, a pixel is related to one and only one element. An exception can be made with glasses and windows or clear water, where you can see through. You've got it also if you get some wall blocking the view too. The fifth one concerns the consecutive aspects. An object is defined as some consecutive matters making it, but sometimes when you take an object in picture, it's split because of obstacles. On the image on the left, there are 2 cars, but because of the wall, the algorithm detects a unique long car. Apart from this kind of exceptions and edge cases, and generally speaking, one object from one image is different from an emitter visible on a spectrogram. The spectrogram on the right depicts a whale vocalization. We can see the harmonics are not formed by consecutive pixels, and yet they are part of the same source we'd like to detect. The 6th concerns I'd like to underline is the serial aspect of sound. We talk about sound events and objects in an image. Because in a spectrogram, events come and go, but in an image, it's a still. A spectrogram is something in between a picture and a video. In music or bioacoustics, there are still a lot of work to be done to address all these issues and their edge cases. Some alternatives could be addressed with recurrent neural network models to avoid unnecessary feature extraction and intermediate representation, for which, in my opinion, transformers are just very expensive and oversized recurrent models. To conclude, I would like to say that I moved from a purely scientific and technical position to a place where I code less and less every day, but I'm thankful to have the chance to supervise an amazing team to work together for self-coordinating coral reefs. We decided with WIFPulse to sponsor these events like the Emerging Bioacoustician Days because it's what our planet needs, some people together gathering to share ideas and solutions. We share a common goal through bioacoustics, monitoring and preserving species and ecosystems. So when it's dark outside and sometimes you lose faith on some technical problems, try to remember what you're working for and that you are not alone. I'm sorry I cannot be there with you, but please reach out to me if you have any questions and check out our news because we will be hiring soon. Thanks for listening, and I'll leave you with our social networks, links, and list of partners that help us make this possible. Have a nice day and take care.
All right, that is it for this morning in the deep learning session. So we can head out to lunch. If you guys don't know where it is, take the stairs all the way next to the entrance to the left. And we start again, I think, in an hour and a half, if I'm not mistaken.